Dear students, welcome to this session. In this session, we are going to learn about three-phase induction motor. What is a three-phase induction motor? First thing is a motor. A motor is a machine which converts electrical energy into mechanical energy. And induction. This particular type of a motor works on the principle of induction. And three phase, already we know that power can be generated in single phase as well as three phase. So three phase induction motor, the machine which converts three phase electrical energy into mechanical energy and works on the induction principle, is called as a three phase induction motor. The three-phase induction motors are the most widely used electrical motors in the industry. They run at essentially a very constant speed, whether you put it on a load or no. So almost it runs with a constant speed. Whenever we need a change in the speed, this is not a good choice. Whenever we need a change in the speed, mostly DC motors are preferred, but most of the industry requires the constant speed, so we can see a heavy usage of the induction motors. And these three-phase induction motors are they are very simple, rugged, low priced, easy to maintain, and can be manufactured with characteristics to suit most industrial requirements. And wherever one disadvantage of this is the starting torque is low. So whenever we need a variable speed or a higher starting torque, different kinds of motors will be used. So in the diagram you can see this is a very simple diagram. RYB three-phase supply is given to the motor, and this motor has a stator, rotor, and it is mounted on the shaft. We will look into all the constructional details of the three-phase induction motor. So how it is constructed? So similar to the alternator, the induction motor has two main parts. One is the part which is a stationary or a static part, and it is called as a stator, and the second part is a rotating part of the machine. That part is called as a rotor. We have a static part or the stationary part, stator, and the moving part, that is called as a rotor. And stator will be having the winding, and that winding is called as a stator winding. And on the rotor again we have a winding, that winding is called as a rotor winding. Again there are two types in the rotor. One is a squirrel cage rotor and the second one is the wound rotor. First we will see how the construction of the stator, how the stator will look like. Stator consists of a steel frame. So it consists of a steel frame. So there are two diagrams you can see, and these all the diagrams are referred taken from the electrical machine, principles of electrical machine by V.K. Mehta and Rohit Mehta. So all the diagrams, problems, most of the equation snapshots are taken from this particular book. So we have two diagram. This is the one simple diagram, and here the rotor stator consists of a steel frame which encloses a hollow cylindrical core made up of thin lamination of steel to reduce the hysteresis and eddy current loss. So normally we use the silicon steel which has a lower hysteresis loss, and we use the laminations whenever we are making the core of any kind of a machine. Even in case of a transformer core, you saw it was done using the thin lamination. why we use the thin lamination? It will reduce the eddy current loss, and we use the silicon steel, so it will reduce the hysteresis loss. Okay. A number of evenly spaced slots are provided on the inner periphery. So this is the inner periphery. You can see this is the inner periphery of the stator. We will have a number of slots which are evenly spaced, and inside this slots the insulated conductors are placed in these stator slots and suitably connected to form a balanced three-phase star or a delta connected circuit. So we will have the slots on the inner periphery, and we place, so this is the same diagram here. We have a slots, you can see a slots, evenly spaced slots, and inside that we can place the conductors, insulated conductors, and they will be connected in such a fashion. Either it will be connected as a three-phase star connection or a three-phase delta connection, and R by B, these are the ends of the connection which is connected to the power supply. That is how the stator is constructed. The three-phase stator winding is wound for a definite number of poles. So when we are doing this winding, we can wind it for a definite number of poles as per the requirement of the machine. Okay. So greater the number of poles, lesser is the speed of the motor. So this particular winding can be made in such a way that we can have a number of poles. Next is the construction of a rotor. There are two types of rotors. One is called as a squirrel cage rotor, and another is the wound rotor. In case of a squirrel cage rotor, it consists of a laminated cylindrical core having parallel slots on its outer periphery. Okay. What you can see in the diagram, there are again two diagrams. This is one simple two-dimensional diagram. So you can see this cylindrical structure, and this whole structure is mounted on the shaft. What you can see is a shaft. Okay, so this is the shaft, and we have two end rings on the both the ends, and this cylindrical structure has a parallel evenly spaced slots in which we put the copper or the aluminum bars. So in this diagram you can see here what you are seeing, these lines, they are the indicators of the copper or the aluminum conductors. So the rotor it is consists of a laminated cylindrical core having parallel slots on its outer periphery. So on the outer periphery of this cylinder we will have the slots, and one copper or aluminum bar is placed in each slot. So whatever the slot we have on the outer periphery, we place one copper or the iron bar inside them, and all these bars are joined at each end by a metal rings called the end rings. So you can see what is the structure here. We have a slots. Inside the slots we place the copper or the aluminum bars, and once we place those copper or aluminum bars, at the end we will have a metallic ring. So you can see this is a metallic ring. All those conductors or the bars are connected together or shorted using this metal ring. So you can see the metal ring is on both the sides. On both the sides the conductors will be shorted. So you can see this is the metal ring, that is called as a end ring. On both the sides we will have the metal ring. So the entire construction, this entire construction, if you see, it resembles a squirrel cage. So that is why we get the name as a squirrel cage, and all the conductors on the rotors are short circuited. So we have the bars, and on the both the ends the end rings are there which will short circuit the all the bars. So what we have on the rotor is a closed circuit of the rotor winding. Next one is the construction of a wound rotor. Wound rotor, it is very similar to the what we just talked about, the squirrel cage. Wound rotor, it consists a laminated cylindrical core and carries a three-phase winding similar to one on the stator. The rotor winding is uniformly distributed in the slots and is usually a star connected. Okay, and on one end this winding is connected together or short circuited using a end ring, and the other end, okay, so here this is the picture, the other end of the wiring, they are connected to slip rings. So you can see this rotor winding, one end is of the winding, three-phase winding is short circuited using a end ring. The other end, they are connected to, each phase is connected to one slip ring. So we have three phases of the winding and we have three slip rings. These for example, R phase is connected to the slip ring, Y is connected to second, and B is connected to the third slip ring. And on top of this slip ring, so you can see these are the slip rings, and this whole structure is mounted on the shaft. You can see the shaft. When this particular rotor rotates, even the slip rings will start rotating, and on top of the slip rings the brushes will rest. Okay, you can see 1 2 3, there are 3 brushes. It will rest on top of the slip rings, and to that brush we connect a rheostat. If you see the construction of a squirrel cage, all the rotor conductors or the rotor winding, it is short circuited. Okay, and whatever the resistance, that resistance is fixed for the rotor. We cannot change the resistance of the rotor winding, and that has certain disadvantages because the starting torque is limited and it cannot be changed in case of a squirrel cage. However, in case of a wound rotor, we are including a resistance in series with each of the phase. So you can see here, this is one phase connected to the slip ring. On the other end we have a brush and it is connected to rheostat, and normally this winding we will be having in the star connected. So you can see a star connected rheostat on the other side, which is connected in series with the rotor winding. So this is a brush, and to that brush we have connected the rheostat. So there are 3 phases of the resistance. So this is how we can include additional resistance, and we can change, since it is a rheostat variable resistance, we can change the resistance of the rotor winding. So next diagram will show you how the actual connection is. So this is the actual connection. These are the rotor windings. On one side it is short circuited using a end ring. So on the one side you can see these are short circuited, the winding is short circuited using a metallic ring called as a end ring. The other end of the phase, they are connected to the slip rings. These are 1 2 3, these are the slip rings, and these slip rings are mounted on the shaft. So you can see these are the slip rings. These are the slip rings. You can see slip rings, they are mounted on the shaft. As shaft rotates, this whole rotor winding and including the slip ring will starts rotating. And what is the contact between the rotor winding and the rheostat is through the brush. The brushes are resting on the top of the slip rings. So as the rotor rotates, slip rings rotate, the brush will be in a constant firm contact with the slip ring. That is how it makes a connection with the external rheostat. You can see here these winding ends are connected to the one end of the slip ring, and on top of the slip rings we have the brushes resting on top of it, and those brushes are connected to a rheostat. That is a three-phase rheostat. This is how we can change the resistance of the rotor winding. And if you see here, the external rheostat, each of this is connected in series with the each winding. If you see, this is the rotor winding. Through slip ring brush, it is connected in series with this particular variable resistance. Second phase of the winding, it is connected in series with this particular variable resistance, and the third phase of the winding is connected in series with this particular variable resistance. So in case of a wound rotor winding, an additional resistance is added to the rotor winding, and we can change the value of the resistance. When we change the value of the resistance, the current will change in the rotor winding, which is used to change the torque and the speed. Next, the advantages and disadvantages of a induction motor. So advantages are, the induction motor, it is very simple and rugged construction. Thus the construction is very simple, and it is mechanically very strong. It is relatively cheap, it is economical, it requires a little maintenance. The maintenance is also less for the induction motor. It has a high efficiency and reasonably good power factor, and it has a self-starting torque. So the induction motor can start on its own. It has a self-starting torque. And what are the disadvantages? We talked about this. Essentially, it is essentially a constant speed motor, and its speed cannot be changed easily. So basically, the induction motors, whether it runs on a low load or a full load, almost it runs with a constant speed. Changing the speed is not that easy. And another problem with this is its starting torque is inferior to DC shunt motor. So in case of applications where you require a very high starting torque, induction motor is not a good choice. So we can go for the DC motors. It can be series motor or a shunt motor, depending upon what kind of application you have. Whenever you need a starting torque as very high, so example is a electric machine, electric train, or a elevator or a escalator. The initial torque required is very high. Once it starts running, electric train or a escalator or a elevator, once it starts running, the torque requirement reduces. But to move the particular machine from the rest, it will require a very high torque. So induction motor may not be a good choice in those cases. Next, we will see the principle of operation. The principle of operation, basically for every motor, we know how the motor works is, motor works on a very fundamental principle, that is, whenever a current carrying conductor or a coil is placed in a magnetic field, it experiences a force. Means whenever you have a current carrying coil or conductor placed in a magnetic field, it experiences a force. Okay, that is how the electrical energy will get converted into force, and the force will result in a movement. That is the mechanical energy. That is the basic principle of the motor. In case of a three-phase induction motor, how it works is, so we have we will go back to the diagram again. Okay, so this is, we can take it as a diagram. We have here the stator. Inside the stator we have conductors. They are connected in a star delta fashion, and that is called as a stator winding. And there is a air gap, and this air gap between the stator and the rotor is very, very small. And just to give the example, what is the it would be in a few or rather in terms of a millimeter, maybe 0.5 millimeter or 0.6 millimeter. The distance between the stator and the rotor is very small, and then we have the rotor part, and rotor part is carrying a rotor winding, and it is a closed circuit, means there is a closed path, whether it is a squirrel cage or whether it is a wound rotor. In both the cases there is a closed path for current to flow, and this whole structure is mounted on an shaft. This is the arrangement. Now what we will do is we give a supply, a supply to the stator winding. When we give a three-phase supply, AC supply, to a three-phase winding, it creates an rotating magnetic field. That we are going to prove. For now, just assume that whenever we give three-phase supply to a three-phase winding, what it will do, it will create a imaginary rotating magnetic field. So you can just assume that how it is done is, when we give a three-phase supply, you can just assume as a magnetic field is here NS, which is rotating, okay, and that particular magnetic field it rotates with a speed that is called as a synchronous speed. What is the synchronous speed? Whenever we give a three-phase supply to the three-phase winding, it will result, the current will the three-phase current will start flowing in the all the phases. That will result in a creation of a magnetic field which rotates, and that magnetic field rotates with a speed. That speed is called as a synchronous speed. And how that speed, how much would be that speed? That speed is decided by the formula Ns is equal to 120 F divided by P. And what is 120 F? F is the supply frequency and P is the number of poles. So I told you this particular winding is wound for to achieve certain number of poles depending upon the number of poles and the supply frequency. So supply frequency is constant. The synchronous speed will directly depend on the how many poles are there. If the number of poles are less, the synchronous speed is high. If number of poles are more, the synchronous speed is less. It's inversely proportional. No, so now what happened? We have given three-phase supply to the stator winding, and stator winding will start carrying the current in their stator winding, and that three-phase currents in the three phases will create a rotating magnetic field. So that magnetic field will start rotating in this space. So we have a very small air gap, and through that air gap it cuts the conductors on the rotor winding. So initially initially a rotor is static. Rotor is not moving. What is moving? The magnetic field is moving. When rotor is static, rotor winding is static, the conductors of those winding are static, and the magnetic field is rotating. So each conductor on the rotor winding will start cutting the magnetic flux. And we know from Faraday's first law, whenever a flux linked with a coil or a conductor changes, EMF is produced. Now the rotor bars or the rotor conductors are experiencing a change in the magnetic flux that will result an EMF induced in those conductors. So EMF is induced in all the rotor conductors or the rotor bars. Now EMF is induced, and rotor winding is a very closed circuit. So there is a path for current to flow. What will happen? That induced EMF will result in a rotor current. So rotor current will start flowing inside all those rotor bars or the rotor conductors. Now what has happened? Rotor conductors are carrying a current and they are placed in a magnetic field. Now We know that the basic principle of a motor is whenever a current carrying conductors are placed in a magnetic field, it will experience a force. Now the rotor conductors are carrying a current and they are inside the magnetic field. So each of the rotor conductor will experience a force, and this whole rotor is mounted on an shaft. That particular force will get converted into an torque. So every conductor on the rotor is experiencing a force, and the torque generated by each conductor is T is equal to F into R, where R is the you can say average radius of the rotor. Okay, so that much amount of torque is created by individual conductor. Cumulative of all the torques, this particular rotor will slowly starts moving, and the rotor will starts moving in the direction where the magnetic field is rotating. So that this motion of the rotor, it is in the direction of the magnetic field. So whichever direction the magnetic field is rotating, the same direction rotor will also start rotating. This can be explained by the Lenz's law also. What is the Lenz's law? Lenz's law states that whatever the cause that is producing it, it will try to oppose that cause. And what is the cause that is making rotor to rotate? The rotating magnetic field is the reason or the source which is, or the source or the cause which is making the rotor to rotate. So it will start opposing that cause. And how it can oppose? By making the relative speed between the both the magnetic rotating magnetic field speed and the rotor speed. If both becomes exactly the same, there will not be change in the flux. Okay, but rotor will never be able to catch with the synchronous speed. Okay, let's say if the synchronous speed is 1500 rpm, the rotor will try to catch up with 1500, means rotor will try to rotate with try to catch up with up to 1500, but it will be slightly less. That is called the slip. We will see that one later. So that is how the rotor will starts rotating. So whatever the supplied electrical energy is converted into a mechanical energy in the form of the rotation of the rotor. Okay, so just to briefly overview what is the principle of operation is, when we have a three-phase induction motor, we give a three-phase supply to the stator winding, which is a three-phase winding, which will result in current in every phase. So there is a three-phase current that will flow in the stator winding. Whenever we have a three-phase current flowing in a three-phase winding, it will create a rotating magnetic field. Okay, we will prove that in the later session. For now, just assume whenever we supply three-phase AC supply to the three-phase winding, it will create a rotating magnetic field. When this rotating magnetic field is created, it will start cutting the, initially rotor is standstill, means it is not moving. It will start cutting the rotor bars or the rotor conductors. They will start cutting the magnetic field, and whenever the flux linked with the conductor changes, and EMF is produced. EMF is produced in all the conductor bars, and since there is a closed circuit for the rotor winding, current will start flowing in the rotor winding. So there is a current in the rotor winding. So each of the rotor conductors or the bars, they are carrying current, and they are placed in a magnetic field. Whenever a current carrying conductor is placed in a magnetic field, it experiences a force. So all the rotor conductors which are on the outer periphery, they start experiencing a force. Since they are mounted on a shaft, that force is converted into a torque, and this rotor will starts rotating in the direction of the rotation of the magnetic field. Whichever way the magnetic field is rotating, it will start rotating in that direction, which is also explained by the Lenz's law. So that is the principle of operation.